Somewhere inside a windowless laboratory on the south side of Chicago, a group of physicists just quietly rewrote the rulebook for quantum computing for the third time in a single month, and almost nobody outside a tiny circle of researchers has noticed. While the tech press was busy chasing headlines about the newest AI chatbot or the latest smartphone leak, the University of Chicago was publishing not one, not two, but three separate breakthroughs that each attack one of the biggest bottlenecks standing between today's fragile, unreliable quantum machines and the kind of fault-tolerant quantum computer that could break modern encryption, design new drugs in days instead of years, and simulate materials that do not even exist yet. If you have been half following the quantum computing race and thought Google, IBM, and a handful of well-funded startups were the only names that mattered, you are about to find out that the most important quantum story of the year is happening at a university. Most people only associate with economics textbooks and brutal winters. And by the end of this video, you will understand exactly why scientists who do not usually get excited are suddenly acting like something huge just shifted underneath the entire field. To understand why this matters, you first have to understand why quantum computers have been stuck in the same place for years, despite billions of dollars in investment and decades of promises. A classical computer, the kind you're watching this video on right now, stores information as bits, and each bit is either a 0 or a 1, nothing else, ever. A quantum computer instead uses qubits, and a qubit can exist in a strange in-between state called superposition, effectively representing 0 and 1 at the same time until it is measured. Pair that with another quantum property called entanglement, where two qubits become linked so that a change to one instantly affects the other, no matter how far apart they are. And in theory, you get a machine that can explore an enormous number of possibilities simultaneously instead of one at a time. That theoretical power is why banks, pharmaceutical companies, defense agencies, and every major tech company on Earth have poured staggering sums into quantum research. But there's a catch, and it is a brutal one. Qubits are almost unbelievably fragile. The tiniest vibration, a stray photon, a fluctuation in temperature measured in thousandths of a degree above absolute zero, can destroy the delicate quantum state a qubit is holding, an effect researchers call decoherence. When that happens, the calculation is corrupted, and the answer becomes garbage. For years, the accepted solution to this fragility problem has been something called quantum error correction, and the dominant method has been what is known as the surface code. The idea sounds simple on paper: spread the information from a single, reliable, logical qubit across many physical qubits, so that if one of them fails, the others can help detect and fix the error before it ruins the computation. In practice, this requirement has been devastating for anyone trying to build a useful quantum computer. Under the surface code approach, protecting a single trustworthy logical qubit can require somewhere in the range of 1,000 physical qubits, and a genuinely useful, fault-tolerant quantum computer capable of tackling real-world problems was projected to need millions of physical qubits working in concert. Millions of physical qubits is not a small engineering hurdle, it is closer to a wall. It is the reason so many experts have spent the last decade quietly admitting that truly practical quantum computing might still be 20, 30, or more years away, even as companies kept releasing flashy demonstrations of processors with a few hundred qubits that could not yet do anything most businesses actually need. This is exactly the wall that the University of Chicago has now hit 3 separate times in the span of a single month, and each hit has left a visible crack. The first breakthrough, the one that actually got a modest amount of coverage from science outlets willing to dig past the usual headlines, involves a new class of error-correcting codes called quantum low-density parity check codes, or QLDPC codes for short, combined with reconfigurable atom arrays built from neutral atoms that researchers can physically move around using tightly focused laser light almost like invisible tweezers. Instead of the rigid, fixed layout that the surface code demands, this approach lets researchers rearrange the connections between qubits on the fly, creating far more efficient error-correcting structures that do not need anywhere near as much redundancy to achieve the same level of protection. The projected impact of this shift is staggering. Instead of needing roughly 1 million physical qubits to build a computer capable of meaningful, fault-tolerant calculations, his new blueprint could bring that number down by a factor of 10 to 20, meaning the same computational power might eventually be reachable with tens of thousands of physical qubits instead of millions. That is not a minor optimization. That is the difference between a machine that exists only in optimistic future projections and a machine that suddenly looks buildable within the current decade using engineering approaches laboratories already understand. Let that sink in for a moment, because the implications reach far beyond academic physics departments. Reducing the physical qubit requirement by an order of magnitude does not just shrink the size of the eventual machine, it collapses the timeline for when industries that have been circling quantum computing from a safe distance can actually start using it. Pharmaceutical companies have talked for years about using quantum simulation to model molecular interactions with a precision that classical supercomputers simply cannot achieve, potentially cutting drug discovery timelines from a decade down to a matter of months. Materials scientists have talked about designing room temperature superconductors or dramatically more efficient batteries by simulating atomic behavior exactly rather than approximating it. And perhaps most urgently, cybersecurity experts have been warning governments for years about a scenario known as harvest now. Decrypt later, where adversaries collect encrypted data today with the plan of decrypting it the moment a sufficiently powerful quantum computer exists, which is precisely why the shift toward post-quantum cryptography has been accelerating across the defense and financial sectors. Every one of those timelines just got compressed, and it happened quietly through a physics paper, not a splashy product launch with a stage and a countdown clock. If that were the entire story, it would already be one of the more significant quantum computing developments of the year. But barely weeks later, before the wider science press had even finished digesting the QLDPC and atom array result, University of Chicago researchers were back with a second breakthrough. And this one attacks the problem from a completely different angle. Instead of focusing on how to protect fragile qubits from errors after the fact, this second discovery focuses on how to generate the powerful, highly entangled quantum states that quantum computers and quantum sensors depend on in the first place. And it does so in a way that researchers themselves described as surprisingly simple. Working with a standard quantum optics setup involving atoms held inside an optical cavity, the team found that making small, precise adjustments to the energy levels of specific atoms, essentially nudging certain pairs of atoms with lasers or magnetic fields so their excited state energies shift by equal and opposite amounts, allows them to generate a remarkably wide variety of highly entangled quantum states without bolting on any new, complicated hardware. Entanglement is the fuel that gives quantum computers and quantum sensors their edge over classical devices. And until now, generating specific, useful entangled states reliably has often required intricate, expensive, and highly specialized equipment. If a research team can instead coax rich, controllable entanglement out of a setup researchers already have, sitting in labs around the world using nothing more than careful energy level tuning, that dramatically lowers the barrier to entry for advanced quantum sensing and quantum information experiments, not just at flagship national laboratories with unlimited budgets, but at universities and companies that do not have billion-dollar research budgets behind them. What makes this second breakthrough particularly interesting is how it complements the first one instead of simply duplicating it. The QLDPC and atom array result is fundamentally about protecting quantum information once you have it, making error correction dramatically more efficient. The entangled states discovery is about generating powerful quantum resources more easily and more flexibly in the first place. Put those two advances toe to ether, and you get a research pipeline that is simultaneously making it cheaper to create high-quality quantum states and cheaper to protect them once they exist, which is precisely the combination the field has been missing for years. Researchers in the community have started comparing this current period in quantum computing to the era right before the transistor reshaped classical computing. A moment where a handful of foundational breakthroughs quietly stacked on top of each other before the outside world noticed anything had changed, and then suddenly everything downstream moved incredibly fast. Now here's where the story gets genuinely strange, because instead of taking a breath after two major results in a matter of weeks, the University of Chicago has produced a third significant advance, and this one has received almost no mainstream attention at all, which is exactly why we are covering it here. This third development comes out of ongoing work aimed at solving one of the most stubborn problems in the entire field, connecting quantum computers to each other over meaningful distances to eventually build what researchers call a genuine quantum internet. For a quantum computer to be useful at scale, it is not enough to build one powerful machine sitting in a single laboratory. Real-world applications, from secure quantum communication between government agencies to distributed quantum computing networks that link multiple smaller quantum processors into something more powerful than any single machine could be alone, require the ability to transmit fragile quantum information across real distances without destroying the delicate states that make the whole system work in the first place. Researchers working on this problem at the University of Chicago focused on individual erbium atoms, which are attractive for quantum networking because they naturally emit light at telecom wavelengths. The exact same frequency is already used by the fiber optic cables that carry internet traffic around the entire planet. The catch has always been that erbium atoms tend to lose their delicate quantum coherence extremely quickly, making them a poor foundation for anything resembling a functional network. In this new work, the team managed to raise the quantum coherence time of individual erbium atoms from roughly 1/10 of a millisecond up to more than 10 milliseconds, with some individual demonstrations pushing that number as high as 24 milliseconds. On the surface, those numbers might sound tiny. We are still talking about fractions of a second. But in the world of quantum coherence, that represents roughly a 100-fold improvement, and it fundamentally changes what becomes possible. A coherence time. That short used to mean quantum information would essentially evaporate before it could travel any meaningful distance through a network. A coherence time, roughly 100 times longer, means researchers can seriously start testing whether quantum information can survive transmission over genuinely long distances using the same telecom infrastructure that already crisscrosses the globe, rather than requiring an entirely new, exotic communication network built from scratch. The research team is already building out the next stage of this experiment inside their own laboratory. Constructing additional cooling systems so they can link separate qubits together through more than 1,000 kilometers of spooled fiber optic cable, essentially simulating what a real long-distance quantum network connecting two distant cities might behave like, all before ever deploying a single strand of fiber outside the building. If that local simulation succeeds, the next logical step becomes testing real distance links, and the researchers involved have specifically mentioned scenarios like eventually connecting a city such as Chicago to a city such as New York using quantum-secured infrastructure built on exactly this kind of erbium-based technology. Think about why this third breakthrough matters just as much as the first two, even though almost nobody's talking about it right now. The first breakthrough makes it dramatically cheaper to build a single powerful, error-corrected quantum computer. The second breakthrough makes it dramatically easier to generate the powerful entangled quantum states that machine depends on. And this third breakthrough makes it realistically possible to eventually connect multiple quantum computers together over real distances using infrastructure that already exists, rather than infrastructure that would need to be invented from scratch at enormous cost. A single powerful quantum computer sitting alone in one building is valuable, but a network of quantum computers that can share entangled states and distribute computations across cities or even countries is an entirely different category of technology. One that starts to resemble the internet itself, except built on quantum physics instead of classical bits. Governments and militaries in particular have been watching this specific piece of the puzzle closely, because a working quantum network is not just about faster computation. It is about communication that is provably secure against eavesdropping in a way that no amount of classical encryption can ever fully guarantee, since any attempt to intercept a quantum signal fundamentally disturbs it in a way that can be detected. So why is nobody talking about this third breakthrough the way they talked about the first one? Part of the answer is simply timing and attention span. The first result got picked up because it directly addressed the most talked about bottleneck in quantum computing, the sheer number of qubits needed for fault tolerance, and it came with a clean, easy to repeat headline number, a 10 to 20 times reduction in required qubits. The second result was interesting to specialists, but was framed as an incremental improvement to existing lab techniques rather than a headline-grabbing leap, even though its practical impact on lowering the cost of quantum experimentation is arguably just as significant. And this third result, the quantum networking advance, is easy for casual coverage to misunderstand or ignore entirely because it is not about building a faster or bigger quantum computer at all. IT is about connecting the quantum computers that already exist or will soon exist, which sounds less exciting on a headline, but might actually be the piece of this puzzle that determines whether quantum computing becomes a genuinely transformative technology or stays a series of impressive but isolated laboratory demonstrations scattered across the world. There's also a simpler explanation for why this third breakthrough has flown under the radar, and it has to do with how attention in the tech and science media landscape actually works right now. Outlets that cover science tend to chase novelty, and after two University of Chicago quantum stories broke in the same month, editors and algorithms alike start treating a third story from the same institution on a related topic as old news, even when the underlying science is genuinely distinct and in some ways more important than what came before it. That pattern repeats constantly across scientific fields, where the first major result in a cluster gets the spotlight, the second gets a smaller mention, and the third, often the one that quietly ties everything together into something coherent, barely gets covered at all. If you have been paying close attention to this channel, you already know that some of the most important developments in technology rarely arrive with the loudest headline. Arrive as the third or fourth story in a sequence that most people stopped watching after the first one. Put all three of these breakthroughs together, and a much bigger picture starts to emerge, one that goes well beyond any single laboratory result. The University of Chicago is not just producing isolated wins, it is systematically attacking every major bottleneck standing between today's fragile quantum prototypes and tomorrow's genuinely useful quantum infrastructure, from the sheer number of physical qubits required for error correction, to the difficulty of generating the entangled states those qubits depend on, to the challenge of connecting multiple quantum systems together over real distances using existing telecom infrastructure. Researchers connected to this ecosystem have publicly compared the current moment to the earliest days of classical computing, before the invention of the transistor reshaped the entire trajectory of the field, noting that history shows breakthrough innovations like this one often take years to move from a laboratory demonstration into industrial scale production, but that the foundational work happening right now is exactly the kind of work that determines how fast that transition eventually happens. It is worth being honest here and not overselling where things stand. None of these three breakthroughs individually hands the world a finished, fault-tolerant quantum computer sitting ready to use tomorrow. Current logical error rates in real quantum hardware still sit around 0.1% per computational cycle, while the error rates believed necessary to reliably run large, meaningful quantum algorithms are closer to 1 in a million, meaning there is still a substantial gap between where the hardware sits today and where it eventually needs to be. Scaling from today's hundreds of qubits up toward the tens of thousands or millions required for genuinely fault-tolerant systems will also demand major advances in manufacturing, wiring, signal delivery, power management, cryogenic cooling, and automated calibration, none of which are solved purely by clever error-correcting codes or improved coherence times on their own. But that honest caveat is exactly why these three results matter so much when you look at them together, rather than in isolation. Each one removes a specific, previously assumed obstacle that the entire field had more or less accepted as a fixed constraint for years. The assumption that a fault-tolerant quantum computer would need millions of physical qubits just got directly challenged by a credible engineering roadmap suggesting tens of thousands might be enough. The assumption that generating powerful entangled states required exotic, specialized hardware just got challenged by a demonstration using equipment already sitting in ordinary optics labs. And the assumption that quantum networking over real distances would require entirely new infrastructure just got challenged by a result showing that existing telecom wavelength technology, paired with the right atomic system, might be able to carry quantum information across the same fiber optic backbone that already spans the globe. When three separate, previously fixed constraints get loosened in the same general research ecosystem within the space of a single month, that is not simply three unrelated papers landing close together by coincidence. That is usually a sign that a field has quietly crossed some kind of threshold where the pace of progress starts compounding rather than crawling forward one incremental step at a time. This is also a moment worth watching closely because of who is paying attention behind the scenes, even while public coverage stays thin. Chicago has spent the last several years deliberately positioning itself as a serious hub for quantum research and quantum industry, backed by state investment, partnerships between the university and national laboratories like Argonne, and collaborations with major quantum computing companies working on hardware, ranging from neutral atom processors to superconducting qubits to photonic systems. Global competitors are not standing still, either, with research groups at Stanford recently demonstrating quantum devices that can operate using twisted light without needing the extreme, near absolute zero cooling that most quantum hardware still depends on. And major companies like Google continuing to push forward with their own large-scale quantum processors capable of tasks that would take classical supercomputers an amount of time longer than the current age of the universe to replicate. The competitive landscape around quantum computing right now looks a lot like the early internet, or the early days of classical computing, filled with multiple approaches racing forward in parallel, none of them guaranteed to be the eventual winner, but each one raising the odds that someone, somewhere, breaks through the remaining barriers sooner rather than later. What makes the University of Chicago's recent run stand out is not that any single result guarantees victory in that race. It is that three distinct, technically serious advances landing from the same research ecosystem within weeks of each other suggests a genuine acceleration is underway, not just a lucky headline or a single well-timed press release. If you have made it this far, you're exactly the kind of viewer who understands why stories like this deserve more attention than they get, and if this kind of deep dive into the developments most people are scrolling past is useful to you, go ahead and hit like and subscribe, so more of these breakdowns land in front of you before they become mainstream news instead of after. The honest reality is that most people will not hear about any of this until a company eventually packages one of these advances into a headline about breaking encryption or curing a disease years from now, and by then it will feel like it came out of nowhere, when in fact the groundwork was laid quietly in papers most people never clicked on, months or years earlier. That is exactly the pattern that is played out with almost every transformative technology in modern history. From the internet itself, to the smartphone, to the current wave of artificial intelligence, all of them built on foundational research that looked unremarkable to outsiders right up until the moment it suddenly was not. So where does this actually leave quantum computing heading into the rest of this year and beyond? The most likely near-term outcome is not a single dramatic announcement of a finished, world-changing quantum computer, but rather a continued acceleration of exactly this pattern. Incremental but increasingly frequent breakthroughs, stacking on top of each other from multiple research institutions racing in parallel, each one chipping away at a specific bottleneck until the combined effect becomes impossible to ignore, even for people who were not paying close attention. Watch for follow-up papers building directly on these three results. Watch for whether other labs around the world manage to independently replicate the QLDPC and atom array error correction approach at larger scale. Watch for whether the entangled state generation technique gets adopted quickly by other quantum sensing and quantum computing groups because it is genuinely easier to implement. And watch closely for updates on that erbium-based quantum networking experiment as the University of Chicago team moves from 1,000 kilometers of spooled cable inside their own lab toward genuine real-world distance tests. Keep an eye on rival institutions too, since a result this significant rarely stays uncontested for long, and competing groups at other universities and companies will almost certainly attempt to match or improve on these numbers within the next several months, which is usually how you can tell. A result was genuinely important rather than a one-off curiosity nobody else bothers chasing. Any one of those follow-ups could be the moment this story finally breaks into mainstream coverage the way the first announcement briefly did. And if you want to actually understand what is happening, when that moment arrives, instead of scrambling to catch up, this is exactly the kind of channel that will have already walked you through it. There is one more thing worth sitting with before we close this out, and it is the uncomfortable question that hovers over almost every serious quantum computing breakthrough, once you start looking closely at the security implications. If a fault-tolerant quantum computer capable of breaking today's most widely used encryption standards is genuinely years closer than most people assumed just a few months ago, that timeline compression does not only matter to physicists and computer scientists, it matters to every government, bank, and technology company currently storing sensitive encrypted data with the assumption that it will remain unreadable for decades. The harvest now, decrypt later strategy already being pursued by well-resourced intelligence agencies around the world, becomes a far more urgent concern the moment breakthroughs like these three start compounding, rather than trickling in slowly one at a time. Which is exactly why the transition toward post-quantum cryptography across banking, defense, and critical infrastructure sectors has been accelerating even faster than most public conversations reflect. None of that means panic is the right response, but it does mean that what looked like a comfortably distant, decades-away problem just a year or two ago now deserves to be treated as a near-term planning issue by anyone responsible for protecting sensitive information, and that shift in urgency traces directly back to quiet university research results exactly like the three we just walked through. It is also worth pausing on artificial intelligence because the connection between quantum computing and AI gets thrown around so casually online that most people have stopped taking it seriously, even though the actual relationship is more concrete than the hype suggests. Modern machine learning models are fundamentally limited by the amount of computation available to train and run them, which is exactly why companies keep building bigger data centers and burning more electricity, chasing marginal improvements. A genuinely fault-tolerant quantum computer would not simply make today's AI models faster. It would open the door to entirely different classes of algorithms for optimization, sampling, and simulation that classical hardware structurally struggles with no matter how many chips you throw at the problem. Researchers have already shown early, narrow examples of quantum approaches helping make certain machine learning processes more efficient, and some teams have explicitly discussed how quantum computing could eventually reduce the enormous energy footprint associated with training the largest AI systems, since certain calculations that require enormous brute force on classical hardware could, in principle, be handled far more efficiently on a sufficiently advanced quantum machine. None of this means quantum computers are about to replace the graphics processors currently powering AI labs around the world. That is not how the technology works and probably never will be. But it does mean that every reduction in the physical qubit requirement, every improvement in coherence time, and every easier path to generating useful entangled states brings that eventual crossover point closer. And crossover points like that tend to arrive faster than cautious public timelines predict once the underlying constraints start loosening the way they just did in Chicago. The medical and materials science implications deserve the same level of honest attention because this is where quantum computing stops being an abstract computer science story and starts becoming something that could show up in an actual hospital or an actual factory within the working lifetime of most people watching this video, simulating how a new drug candidate will actually interact with a specific protein at the molecular level is a calculation that grows exponentially harder as the molecule gets larger, which is precisely the kind of problem classical supercomputers handle through approximation rather than exact computation. often missing subtle interactions that only become obvious after years of expensive trial and error in a physical lab. A quantum computer, capable of modeling those molecular interactions directly, rather than approximating them, could in principle compress years of pharmaceutical research into a dramatically shorter window, and the same logic applies to designing new battery chemistries, more efficient solar materials, and room temperature superconductors that have remained frustratingly out of reach using classical simulation alone. None of that arrives the day a fault-tolerant quantum computer first switches on. These applications require not just raw computational power, but new algorithms specifically designed to exploit it, plus years of validation before any regulator or manufacturer trusts the results enough to act on them. But every one of those downstream possibilities depends entirely on the foundational hardware problems that these 3 University of Chicago breakthroughs just started chipping away at, which is exactly why physicists working far outside the field of quantum computing itself are quietly paying close attention to results like these, even when the general public has not caught on yet. None of this is worth taking on faith either, and if there is one habit worth building as this field accelerates, it is learning to separate a credible engineering roadmap published in a peer-reviewed journal from a marketing headline designed to move a stock price. Everything discussed in this video traces back to published research and statements from the scientists who actually did the work, not speculation dressed up as certainty, and that distinction matters enormously in a field this hyped, where genuine progress and inflated promotional claims often get reported using nearly identical language. If a channel or an article promises a working, world-changing quantum computer next year, that is a signal to be skeptical. If a result instead quietly removes a specific, previously fixed technical constraint the way these 3 did, that is usually the far more meaningful signal, even when it does not come wrapped in dramatic language, and learning to spot that difference is exactly what separates people who understand where this technology is actually headed from people who are only reacting to whatever headline crosses their feed that day. If that distinction is useful to you, that is another good reason to like and subscribe, because separating real signal from noise in fast-moving science stories like this one is precisely what this channel is built around. Step back and look at the full picture one more time before we wrap up. In the span of roughly a month, a single research ecosystem centered at the University of Chicago produced a credible engineering path to slashing the physical qubit requirement for fault-tolerant quantum computing by a factor of 10 to 20. A surprisingly simple new technique for generating the powerful, entangled quantum states that both quantum computers and quantum sensors depend on using equipment labs already have, and a 100-fold improvement in the coherence time of telecom frequency atoms that could eventually allow quantum information to travel across the same fiber optic infrastructure already wrapped around the entire planet. Any one of those 3 results on its own would be worth a headline. All 3 landing together, quietly, within weeks of each other, from the same broader research community, is the kind of pattern that historically shows up right before a field stops moving in slow, predictable increments and starts moving in ways that catch almost everyone off guard. Nobody knows exactly when that shift fully arrives, but based on what just happened in Chicago, it is looking a lot closer than most people currently think, and you now know about it before almost anyone else does. If you want to be ahead of the next one of these moments instead of hearing about it secondhand months later, make sure you are subscribed, because this is exactly the kind of story this channel exists to catch early. And there is a very good chance the 4th breakthrough in this same sequence is already sitting quietly in a preprint somewhere, waiting for someone to notice it.